First up, we have Nejmie Oze, and she is an expert in linear dynamical systems, dynamical systems in general, and she's a professor at University of Michigan, and can't wait to see what she has in store for us.
Thanks. So I am going to try to give you some perspective from a control theorist and partial practitioner view of what I think about, how I think about control and how I think about learning and how things come together. Then I will talk about some work that we recently did with Samet Oymak from UC Riverside. So that's going to be the technical part of the talk. So I will start a little high level, and I will try to show you the type of problems that I work on and the type of problems that I care about. So I work a little bit on control of safety-critical autonomous systems. And typically, we have high-fidelity simulations. So these are like two systems that I work on. One is autonomous driving. This is a simulator from CarSim, and industry uses this simulator to test their algorithms. The other example is autonomous taxiing for an aircraft. Again, that's X-Plane. It's an industry-scale simulator. Very complex models, but there are models in there. And we try to do control design for systems, typically with constraints. And one thing that's interesting, when I start working on these problems, you learn interesting constraints. For example, if you are trying to make an aircraft park, I don't know if you're aware of this, but aircrafts cannot back up. They can only go forward. So if you screw up something, then you cannot back up and recover. The truck needs to come and pull you back. So the constraints are kind of important. When I get a little adventurous, I try to put things on real machines. So we have a test track at the University of Michigan. Actually, that simulator has a model of the test track. We call it MCD. And this is a self-driving car running one of the controllers that we automatically synthesize. So when I play with real systems, so at Michigan, I wouldn't say I am the person that plays with the real systems the most, but I feel like I learn about certain things that I can put in the theory and reason about. Finally, I collaborate with lots of people doing applied control in different domains. And there are these domains where it is hard to get on-policy data. So one of these domains is smart grid. You have this large grid systems. You have a bunch of loads, maybe thousands, hundreds of thousands of loads that you can coordinate if you have a Nest-like device. But there's also lots of things going on in the grid, other loads coming on and off, that you might have data, but you cannot control. And the thing is, even if you come up with a policy, scheduling policy to control these loads, it's hard to test that scheduling policy on the real system. And here is another data, again, in the context of driving. If you're at Michigan, you cannot avoid working with cars. So this is data collected over a highway. So this is like, there's, I think, a month-long data. They equip the highway with cameras. They are tracking different vehicles. And for example, if you want to design an autonomous vehicle, you want to learn how people react, for example, if a car is overtaking them. And we have these type of data, but it's hard to get on-policy data or put your autonomous vehicle without knowing anything into the highway and expect that people will let you do that. So that's why models are central to most of the things that I do. So I always think about going from data to models and models to controls. So models is always in the middle, so I don't understand that much about model theory, but I am willing to learn and how it can help in the control context. And typically, we have this type of models. It could be nonlinear dynamics. We have some observations. Why? We typically have some noise uncertainty models, and we have some control constraints in how we pick our controls. And on the from data to model side, I look at problems like system identification. If I have input-output data, how do I learn a model of this form? So that's one of the problems that I am going to talk on the technical part of the talk. I care about model invalidation. I have model now, and I am collecting more data, and I want to say something about whether this model is a good model. Is it still representing the data or not? And if I can answer those questions, I can also do fault detection, anomaly detection. So if this model is a good model of the world, and I keep collecting data from the world, and if something changes in the world, based on this model, I can do those type of analysis. So those are the things where models plays a role in what I do. And from model to control part, I work on formal verification and control synthesis, where we look at decision problems of this form. Does there exist a control policy? Sometimes we restrict the policy class such that X holds. And this X could be stability of the closed loop, existence of some inductive invariant, if you want to prove safety, achieves a task. My closed loop system achieves a task described by an automaton or some temporal logics. It could be reachability or those type of things. And the type of answers that I want to give is I either want to give a yes answer, and whenever the answer is yes, I want to have an algorithm that automatically generates this control policy. Or in some cases, I want to give the no answer together with a certificate and proof of non-existence. So that you know with this model class what you are trying to achieve is impossible, then you either ask your system to do less, or you add sensors or actuators so that your system is more capable if you want to do that specific thing. As it turns out, if you write down nonlinear dynamics of that form, these decision problems, even the simplest ones, are undecidable. So we try to understand, are there decidable subclasses here? And the other thing that we try to understand is if we have something that says yes and no, what is the gap in between if we cannot close the gap?
How of the model is model?
What's that?
How are you describing the model? But the input is a model, and the output is a yes or no, right?
So input is a model.
Right, and how does the model look like?
It looks like that in the most general form.
How can I access the model then? It's that abstract.
I think it's later.
Oh,
in the
so
talk.
it's
Okay,
physics.
it's later in the talk.
Oh, nice.
What's
Pause.
that?
I know I'm saying like probably later in the talk you're going to talk about F.
Yeah, I will specify what type of, but this is more high level. F could be your physics, and you know how to write down your F equals MA and get those.
Do you chain these together and talk about how much data you need in order to provide either yes or no certificate? Do you talk about how much data you need in order to provide a yes or no certificate?
So that's what we are trying to do, but I don't have answers to that yet. And I think this community can help.
It's the model, right? You have a model. The certifications
So-
of the model, not from the data.
I'm asking if you can chain them. So can you go all the way? One question we've been interested in is how much data do you need to identify what V star is in a class? And so I'm curious if you can say, given this data, and then you chain it through a model, how much can you answer? How much data do you need to answer if a controller exists?
So the thing that I am going to talk about is how much data do I need to learn the model with a certain accuracy. And the thing that we know how to answer for very simple classes of problems, very simple classes of models, and very simple classes of X's is how much uncertainty in that model I can tolerate so that my answer is yes, no. But general solutions don't exist. And we always go through the model. I don't personally know how to go past the model and have the data and have the task on the other hand. So things that I like models because I know how to ask this decision problem, and in some cases how to answer that decision problem if I have a model. I also like models because I want to have the ability to change my control objective. So today I might be interested in this, but if I see that something is, the answer is no, then I might switch to an alternative objective. So that's why I also like models. If I have the model in the middle, I can change the objectives and look at the yes/no answer. And this is the question I was trying to pose to some people at lunch. Say I have a model. If I get more data, I know how to check the validity of my model and therefore the validity of the controller. But it's a little hard to do validation from data for a policy if I just have the policy. That's probably related to Emma's talk. I don't know in most of the settings that I am interested in how to use off-policy data, additional off-policy data, to reason about my existing control. But if I have the model in between, I can reason about validity of my model in the middle. So the other thing that I like is, what was there a question? The other thing that I like is constraints. Constraints rather than objective functions. And I would argue specifying certain tasks with a single reward or cost function is typically hard. And this is something when I talk to people in more applied domains, they also complain about. They are having trouble in, for example, they are doing MPC, but they don't really know how to pick the cost function in the MPC. And they say they do lots of model tuning and they do lots of cost function tuning as well. So you can say, oh, I can append my constraints to my objective function, get an indicator function type thing for my constraints, put it in the objective. But nice additive quadratic cost functions that we really understand well, theoretically, they are no longer enough. Yes.
Can you explain a little how you think about constraints? So I can think about constraints such that I really need to respect this constraint at all periods while I'm training my policy. Or I can think of constraints where eventually I want to discover a policy that satisfies these constraints. And the distinction maybe matters a lot if you're actually acting in the real world. So I'm curious, how should I think about constraints?
So there are both. So one type of constraints we care about is this inductive invariance. So there is an unsafe set. You don't want to crash your car. You don't want your robot to fall. And you want to find a subset in your state space that you can guarantee that you remain in that subset. And if possible, you want to find the maximal such subset. And for invariance type properties, the maximal exists. It's unique. But if you have something different like reachability, then that uniqueness of the initial conditions, it's that the maximal initial conditions is not unique. And it could be objectives like reach avoid. You want to reach a certain state while avoiding something. So this is, you can think about it as a spatiotemporal constraint that you want them to hold. Okay, so these are some perspectives. And there are, I see two different ways people approach data in control, and there are two different regimes. One regime where we have this very complex models. For example, the high fidelity simulations that I showed earlier, they have super complex physics. They have this PDE model. Sometimes to simulate 1 minute of reality, you need to wait a whole day because your finite element model and PDE solvers are cracking a bunch of things. But this complex model, you can think about it as an infinite data set. So you can set certain parameters and get a bunch of data from it. And we can also collect lots of data. And system identification is a way to learn some simple models from these complex models. All the people build these complex models. They never use them for control. For control, you try to get a much simple model. For example, if you want to test a flight controller, you test it on a simulator that has all the finite element model of the wings, but the model that you are using is just a Newtonian model and very simple models on the physics of the aircraft. So And if I can learn this simple model, I can do multiple things. As I said, if I have a simple enough model, I can do control design. If the model is complicated, even if you give me this model, we don't know how to do control design. This is nasty, nonlinear. But for some simple models, we know how to do control design. We can do fast simulations. Sometimes you want to do faster simulations. And with those fast simulations, you can do system monitoring type things as well. So simple models are useful in that sense. So, but this is thinking about where you can get lots of data. And people thought about this problem. There's also this other regime where we only have small data. So if you are exploring unknown environments, you cannot collect data. You just go to the Mars, and you are there. You are getting data for the first time, and you want to do something with that. Or handling an unexpected failure. So if something fails when you are in flight, then you need to learn something fast so that you can react to what failed. And in this case, online system identification becomes important. You don't have batch data, and you want to learn these models at runtime. And I still like having models because I can adapt. So I can change my mission objectives. If I figure I lost lots of things in my aircraft, maybe I just want to land now. I don't care about reaching my destination. And having models will help with those type of things. And in this talk, I will talk about this small data regime. And I will use a very simple model class. And I will talk about how to learn that model class. So this is the type of models I will try to learn. Given some input-output data, U and Y, we want to find a model of this form, where there's A, B, C, D matrices. There's some noise, both process noise and measurement noise. And in system identification literature, people looked into this problem. And again, I said there's this large data regime and small data regime. And depending on which regime you're at, you're interested in different type of analysis. So most of the early work in system identification reason about asymptotic analysis. As the data size goes to infinity and the noise level goes to 0, can we learn the system model? What is learnable in this system model? And if there is something learnable, can we learn it? Is there an algorithm? And more recently, people started looking into this non-asymptotic analysis where you try to reason about finite amount of noisy data. And you want to understand how your identification accuracy depends on the data size. And you are also interested in lower bounds in this regime as well. So there is quite a bit of work in both areas. For asymptotic analysis, if you open up a system identification book, there are lots of standard methods. And we understand very well how they behave asymptotically. And for non-asymptotic analysis, there was an interest in the topic from control theorists back in the days and also recently. And there's this nice survey paper, if you are interested in, that came up last year that summarizes what has been done for non-asymptotic analysis in the control setting. And there's also this new statistical machine learning type methods. Ben worked on it quite a bit. And we are inspired by these type of methods. But there is one thing I would mention. There are different assumptions both in this work and in this line of work, and we are trying to relax those assumptions. For example, old control theoretic methods, they have this assumption of noise invertibility, which roughly means if I go back to my model, if I give you A, B, C, D, and if you observe Y and U, you should be uniquely recover your noise, which doesn't hold in this case. But if you have that property, then there are quite a bit of techniques out there to do non-asymptotic analysis for that class of models. However, even for the simple model that I showed, that noise invertibility does not hold. Then there's the statistical machine learning methods where people come up with different algorithms for doing system identification, again with some simplifying assumptions from the perspective of what we are learning. But they do very deep analysis reasoning about statistical properties of what is going on. So what we try to do is we try to just pick these traditional algorithms that people use in practice and try to understand whether we can do non-asymptotic analysis on them, rather than coming up with a new algorithm. These are algorithms used in practice, and can I take that algorithm and reason about it? So the contributions of this work is this related to this Ho-Kalman algorithm. I will explain what Ho-Kalman algorithm is. And we develop a way to understand noise sensitivity and noise robustness of this Ho-Kalman algorithm. And based on that, we give this non-asymptotic learning results on Ho-Kalman. And Ho-Kalman, it's also known as eigenrealization algorithm. Ho-Kalman is the version that's noise-free. When you have noise, it's called eigenrealization algorithm. And it has these properties. So it learns from input-output data. So you cannot measure your state, because when you measure your state, the problems become a little simpler. At least the identification problem becomes very simple if you don't have noise. But we want to learn from input-output data, so this brings two challenges. This is a generically ill-posed problem, and I will tell you why it's ill-posed. And we can only learn some canonical representations because it's ill-posed. I can learn up to something. So we are trying to learn from single trajectory, so I don't have the luxury to run multiple experiments in the settings that I am interested in. And this brings some difficulties in doing the statistical analysis, because you have dependent data and you want to reason very carefully about your dependent data. And as I said, the results from the control community doesn't apply in this case, because for the simple model that we have, that noise invertibility assumption does not hold. Okay. So what does Ho-Kalman algorithm do? Ho-Kalman, when they came up with this algorithm, they thought about this noise-free setting. So you have some linear model of this form. And before I explain the algorithm, I will mention this is an ill-posed problem. Can you see why it is ill-posed? So if you can
always change the state by multiplying this in an invertible matrix and then reverse that thing with C.
Exactly. So if I define a new state x tilde, I don't observe the state. I can rewrite the dynamics. Now there's a new C, new A, new B, new D. But with the same input, it will give me the exactly same output, assuming if I do a transformation to my initial condition as well. So we cannot learn A, B, C, D. We can only learn up to a similarity transformation. The other thing is that we can only learn controllable and observable part of the system. So this is something we understand in control really well. So we will either assume the system is controllable and observable, or you can also infer from Ho-Kalman the controllable observable part of your model if your model is not controllable and observable. Okay, so given these assumptions, how does Ho-Kalman work? It's a two-step procedure. You first estimate the so-called Markov parameters of your system. And Markov parameters, they are also known as the impulse response of the system. And one thing to note, these Markov parameters, they are invariant to the change of basis. So if you look at this CB, CAB type terms, if you look at CB, if I have this updated C, my CB is still the same. So this is something I can invariantly learn independent of my state representation. And in the second part, what Ho-Kalman does is that it estimates system matrices from these Markov parameters. And I will show you how these two steps works and how the error propagates through the two steps. So any questions so far? We are good? OK, so in the first part, I will talk about how to estimate the system matrices, given that you know your Markov parameters. So Hankel matrices came up during the workshop yesterday. So this is where Hankel matrices pop up in control. So if I have these Markov parameters, I can form this Hankel matrix. And one observation about this matrix is that this matrix has a factorization of this form. And if you look at this factorization, this is essentially your extended controllability matrix, extended observability matrix, and that's your extended controllability matrix. And one thing we know from that is that if my system is controllable and observable, the rank of this matrix is equal to n, when n is the state dimension. So how does Ho-Kalman proceed from this Hankel matrix to obtaining a set of A, B, C, D, and why this set of A, B, C, D is a nice one? So what you do is that you get rid of the last block column of your Hankel matrix. You take this matrix that, let's call it H plus. You take this. You get rid of the first column of your Hankel matrix. You take this other matrix, let's call it H minus. And one thing you can see is that H plus itself is a Hankel matrix for your system. So it's a multiplication of some extended observability matrix times an extended controllability matrix. And H minus is the same observability and controllability matrix with an A in between. And we have this, and from that, we can figure out what A is. So the algorithm goes like this. You take your H plus, you factor it out. I am writing SVD there, but that SVD in the noiseless case is exact. Then you set your O to be the left side of your SVD, Q to be the right side of your SVD. Then you can extract the C bar, B bar, A bar. That essentially gives you a realization of the system. And there is something special about this realization. This is called a balanced realization. Balanced here means each state or each mode of this system or each eigenvector of this system is such that it's as controllable as it's observable. So this also helps you to do select your model order if you do it this way. So it's kind of not parameterized. So you are not fixing the model order, and model order comes out of this analysis. And that singular value decomposition, the sigma that I have there, they are called Hankel singular values, and those are related to certain properties like H infinity norms of my system model. So this is what happens when you have exact Markov parameters, but we won't have exact Markov parameters. As I said, we will just estimate our Markov parameters. Now, instead of G, this matrix of Markov parameters, I will have some estimated Markov parameters. And to our surprise, this is used a lot in practice. This is a name, eigen realization algorithm. And I talked to a bunch of senior system ID people. We were like, oh, there should be an analysis, like people are using this. How does noise propagate through this algorithm? And there wasn't any. So the first thing we did is, let's try to understand how noise propagates through this steps of SVD, picking O head, C head, B head, A head, like this. So the difference here is that The main difference is that my SVD, it used to be exact. Now I am just truncating at n. So let's say I have an estimate on, or I have a bound on how far away my Markov parameter estimates from the true Markov parameters. How good would be the estimates that I obtain from this algorithm? So this is...
So the bound holds for any index t? So the
But we will fix capital T.
okay.
You make it big enough.
And I will come back to that. I have some issues with the T there, but it's a different story. So the two results we have is if I have some estimate G hat, then I can bound the spectral norm of the error between H and H hat. And based on that, I can bound the spectral norm of the error between L and L hat.
All these are spectral norms?
Yes. It's not the best, but the math works out easier that way. And if we further assume the error is such that it's smaller than the minimum singular value here, it's just saying my smallest mode is controllable and observable enough compared to the error that I get here, then there exists a unitary matrix P such that the ideal balanced realization is close to the CB A hat I compute through this algorithm multiplied with the unitary matrix. And these are the type of bounds you get on A hat, B hat, C hat estimates. Yes?
So it seems that B and C are fine, and with A we have this divide by the minimum eigenvalue, which might bother some people.
This is real.
It's like just a bad thing.
This is real.
Yeah, it's real. Yeah.
It's even better.
It's
just bad.
it's not zero.
Sure.
So it's like, so what we are assuming here is that there is this controllable and observable part of the system. And if your noise, you should pick, this essentially tells you how you pick your model order.
So N is the model order, right? N is the chosen model order term?
Yes.
Yes, N is the chosen model order. That's your parameter. You get to pick it.
Yeah, if you pick your N wrong, so if your noise is overriding your semi-uncontrollable, semi-unobservable modes, then you cannot learn. And if you pick N wrong, meaning your noise level is sort of overriding what you can observe, then you don't expect to learn anyways. But if you pick your N right, then this won't be small, assuming your noise level is comparable to your, sort of this is telling you identifiability, the level of identifiability of the system. Okay.
One more question. T1, T2, that's the shape of the Hankel matrix, is that right?
Yes.
So why not? Why wouldn't you just pick it really long? There must be a downside to picking T1 equals 1. Oh, you want N to be large, so it has to be at least N.
Yes. Okay, so if we somehow estimate G hat good enough, then we can learn our balanced realization good enough. Now the question is, how do I estimate G hat? So one thing you can observe is Markov parameters are essentially equal to this quantity. This would be useful if I had independent trajectories so that I can take this expectation by just averaging. But I have only a single trajectory, so it's not easy to compute this expectation from the data. So for that, what do we do? Again, we consider, given this single trajectory, we consider n subsequences of my data of length t. And one thing I can observe here is that this y capital T here is a function of x0 and the u's that I have up to time t. Then I have these subsequences, this y capital T plus 1. I can write it as a function of x1 and the other u's and so on. Then I can essentially represent this yt in terms of xt minus capital T, my input terms, which I know, and some noise terms that are my process noise and measurement noise. So I can just vectorize everything to write it in a more simple way. I have my Markov parameter matrix multiplying the vector of u's, some f matrix that's a truncated version of this Markov matrix multiplying process noise, my measurement noise, and then extra term et, which essentially captures the effect of this non-zero initial state from the past. And we can characterize the statistics of this thing and treat it as noise. Then once you have this, we just use least squares. And we estimate a g hat. And this is something you can solve in closed form.
Why is it okay to take ET as the zero mean noise, essentially?
Stable system. E tries to stay to zero.
It's zero mean, but the covariance is. Yeah.
Oh, I think that's important. Yeah. Here the idea is that you're driving the system with noise.
Yes,
Process noise, and also
U is Gaussian. U is a Gaussian that I know. Sorry, I forgot to. That's one of the questions that I left for the future. So now, if this is my estimation scheme, which is used in Ho-Kalman, how good is this estimate? Then, so if this is the theorem, given input-output data from a process of this form, where A is stable, and initial state is 0, that's easy to relax. If I am picking my U as Gaussian, and if my noise, process and measurement noise are Gaussian, then if I pick n larger than this quantity, then with very high probability this error is bounded by this quantity. So there's a more refined version of this in the paper, but essentially your noise terms hit you, and if your signal to noise ratio is low, you gain things, and this is how much data you want to have. So with this, we can combine this, and given any delta and epsilon, we can find a tight enough n bar such that if we collect input-output data for n bar steps with probability 1 minus delta, we can estimate the system matrices with accuracy at most epsilon, and you can pose the opposite statement as well. And there are several extensions of this. You can estimate the H infinity norm of the error because we are using Ho-Kalman and because we have Hankel singular values. We can estimate the system order, and we can give you conditions under which you can do this. So I have some numerical examples how it works, and we compared this to something else Samet worked on. So one observation Samet had, he was looking into nonlinear version of this problem where your state update goes through a nonlinearity, more in like recursive neural networks with ReLU type activation. And he said, if I separate these trajectories, and instead of taking this overlapping trajectories, and if my system is stable, I can almost treat these two as independent. Then I can do an easier analysis on that. The analysis is easy, but this is how the practical performance changes if you start doing separation. So we have something that practically better makes use of the data, and it has similar tight statistical bounds.
Why, can you go, why is the dependent going up in all four graphs?
I don't know.
No, but it's always the same, right?
Yeah, that's the trajectory. Huh? What are you
Right, so look at the gray.
Yeah.
regression?
Yeah.
No.
Should be fluctuate.
No, because there could be something systematically biased.
And these are some of the results for different noise levels. And we are looking into relative H infinity error and how this algorithm performs in those cases. So with this, I will conclude with a summary and some future directions. So we provided a sensitivity robustness analysis for Ho-Kalman. From this sensitivity analysis combined with this estimation error on the Markov parameters, we have the sample data guarantees on learning. So given a finite amount of data, how accurately I can learn my system models. There are a few interesting future directions. So can we analyze other system identification techniques? One very popular one is AND4SED. It's used a lot. It's more complicated matrix operations, so we don't have an analysis for that. Is there any value in doing input or experiment design? We are running this with Gaussian, but if it wasn't Gaussian and I can design the inputs, can I do better? And the other question is, when you talk about input design, there are two different input design problems. One is you can design an open loop input. So you design your inputs and you apply it to your system without doing any online update of your input. Or you can design an input policy more similar to online learning setting, where your input policy now decides on what input to apply at the next step. And I don't know if this will gain you anything in terms of sample complexity. Maybe people in the audience might have thoughts on that. And we are also looking into control design type problems so that when we have this yes-no answers in the end, we can say something about the probability of correctness of those yes-no answers. With that, I can.
Do you make any assumptions on stability of your model?
Yes, model is stable.
What's stable?
Yes.